This is discrete math, my first question, doing past paper. So for this paper, it was a lot of heavy definition and proofs. I think that's kind of expected. So in the first question, we have define what it means for a relation proceeds on a set A to be pre-order, partial order, or total order. So, okay, we're going to just get into the definition of these three terms, right? So before explaining what they are, there's kind of four main properties for relations that kind of need to be explained before we can kind of define what pre-order, partial, and total are. So the first one is reflexivity, which basically means that for all x that is part of A, x precedes or is the same as x. This is just basically itself, right? For transitivity, what it means is that for all x, y, z, that is part of A, if x precedes y, y precedes z, then x precedes z. That's what it means to be transitive. For antisymmetric, we have x, y is part of A. If x precedes y and y precedes x, then x equals y. If it's symmetric, it doesn't mean that it's like the negation of this. It's rather just if it's symmetric, then if x precedes, if x is r a, um, if a r b, then b r a. So the idea that it's symmetric. It's the same as if x is precedes y, then y precedes s, sort of in that sense. And then the third last one is comparability, which is also called strongly connected, which basically means that for all x, y, either x is precedes y or y precedes x, one of the two. So we can definitely compare. That's what it means. So in terms of A, like the order, pre-order basically means that it's reflexive, intransitive. If it's partial order, then it's reflexive, antisymmetric, and transitive. If it's total order, then we can compare every set pair of element is pairwise comparable, so it's strongly connected. Yeah, so something to remember is pre-order requires the least amount of conditions. It's just pre, right? So we can think of it as reflexive and transitive. Partial as the antisymmetric part, and total is just comparing pairwise. Okay, for BI, we have show the following relations on sets are partial orders, but not total orders. So the set Rn with elements A equals A1 all the way to AN, with the relation A precedes B if AI is smaller than BI for each I from 1 to N. Okay, so for this, if we're going to have to prove, we're going to have to do it in kind of two parts. The first part is just proving that it's a partial order. And then the second part is proving that it's not a total order. So for the partial order proof of the first statement, set Rn with relation A precedes B if A is each element of AI is smaller than BI. Reflexive, it's true because AI is smaller than equal to AI, right? Because it's equal, hence the statement is holds. Next is the transitive property. Transitive means that if A is smaller precedes B and B precedes C, then each element of BI is smaller than AI is smaller than BI and BI is smaller than CI. So AI is smaller than CI. So A is precedes C. So yeah, that's true. And then the final property that we need to check is antisymmetric. So if A precedes B and B precedes A, then that must have meant that A is smaller than equal to B and B smaller than equal to A. So then that must have meant that A equals B in this case. And then we're done with our partial order proof. And for our total order proof, we would have to show just a counterexample in general. Suppose we have something of this form where A is 1, 0, 0, 0 something, where and B is 0, 1, 0, 0, 0 something. So for our first term, A1 is greater than or equal to B1, but in our second case, B2 is greater than or equal to A2. So then neither of these situations holds, so a it's not a total order. And for part two, we're asked to find set of polynomials with real coefficients where p precedes q if px smaller than or equal to qx for all x in R. So yeah, same idea. We're going to have the partial proof, partial order proof, then not the total order proof. So reflexive for any polynomial p, px smaller than or equal to px, that's true, right? It's just basic whatever is whatever. Next, we have transitive. Basically, that means that if px is smaller than qx and qx smaller than rx, then px is smaller than rx, so p precedes r. And then for our third condition, antisymmetric, if px is smaller than qx and qx is smaller than px, then px equals to qx, so p equals q. So yeah, it's pretty straightforward for partial order proofs. And for total order proof, we can just show that, okay, if px was equal to x and qx was equal to 0, then we can kind of think of it, okay, yeah, we have a constant function. If it was positive, then it's greater. If it's negative, then it's less. So it's not comparable, right? So that's the idea. Just show with one counterexample is good enough. And then for part C, I were asked, suppose proceeds as a partial order on set A and let S be part of A. To find what it means for an element to be 1, the maximum element of S, and 2, the least upper bound of S. So CI is again definition. So if you know it, you know it. If you don't know it, then better just know it now. So maximum of S basically means that there is element M in S, such that for every element X in S, X it precedes M. And then for the least upper bound, what it means is that for an element, let's call U in A, such that U is the upper bound of S. So basically for all X in S, X precedes U. And then if V is any other upper bound of S, then U is smaller than V. So basically the idea is that it's the least one. And it's the upper bound. So yeah, so when you're proving it, you need to have the least and also the upper bound. And then for part two, we have for the least upper bound for the subset, we have this with the standard order smaller than or equal to on R. Prove that the value you obtain is the least upper bound and show that is not the maximum element of S. Okay, so for this, we have this thing, right, of what we just have. This rewritten can be written as 3 minus 2 divided by n plus 1. So we know that as n goes to infinity, this number would approach 3. And this would be our least upper bound. And the proof for this is the shown below. Basically, we want to show that 3 is an upper bound. So for any n that is a natural number, since n is greater than 0, then 2 divided by n plus 1 is greater than 0. So 3 minus that would be smaller than 3 minus 0, which is 3, right? So 3 is the upper bound here. Um, and to show that it is the least upper bound, then we suppose that u is equal to 3 minus epsilon, where it is a smaller bound for epsilon greater than 0. And then we're going to show that, okay, if it's in this case, we can write it in this form, right? So it must have meant that this inequality holds. Rearranging that, we get that n is greater than this. So we're just going to set that n is equal to this, right? We're just going to take the upper bound for that. So it's definitely greater than this. So we're going to plug n back into the sequence, and we're going to find an element that is greater than 3 minus epsilon. So we contradict the assumption of the upper bound, since before, if 3 minus epsilon was already thought to be the upper bound, and if we come to a better optimal solution than that, then that means that there is a contradiction and it doesn't hold. So definitely 3 is the least upper bound. And then the final part asks us to show that 3 cannot be the max. Basically, for 3 to be the max, actually, it needs to be an element of the set S. But because 2 divided by n plus 1 equals 0 has no solution, hence 3 cannot be in the set S, so S has no max. So that's the idea. Okay, now part D. Let R and S be two equivalence relations on set A. Define a new relation R and S on the set A to be such that XY is part of A, X, R, and SY if both XY, XRY, and XSY hold. Denote by A R the equivalence class of A of the equivalence relation R. Show that R and S is an equivalence relation. Okay, so to show equivalence relation, you have to show that it's reflexive, symmetric, and transitive, right? So we're going to do exactly that. For reflexive, we're going to let X to be element in A. we're going to have R and S are equivalent relations, so this is true, right? So since both of them are true, then X, R, and S, X holds. Next, for symmetric, we assume that X, R, and S Y holds. So then XRY and XSY holds. By symmetry, because R and S are shown to be true, these are true, right? So then hence Y, R and S, X holds, so it's symmetric. And for transitive, we're going to assume that X and Y and Z hold for this equation relation. So then these four things hold, right? Because each one we just apply it. So we get four things. By transitivity of R and S individually, we have XRZ and XSZ. So then that means that combined together it holds. So yeah, pretty straightforward, I'd say. Part two, we're asked to show that this um, the equivalence class of A of the unequivalence relation R and S is equal to the just each one N together. So it's just breaking it down into two parts. So what we can do for this is we just kind of just go by the definition, right? Equivalence class of a relation R um, is this. And this basically means that it's the bucket holding all of the elements X that are related to A. So we know that by definition, um, this kind of holds, right? It's just another way of writing. If X is an element of AR, then XRA, right? This is just definition. So then inside our scenario, when we have X is a part of this thing, then we know that XR and SA is the same, equivalent, that's interchangeable. So then we can further interchange this with the idea that, okay, we just know that this, so we can just break it apart from the definition of the intersection, right? We just did this so many times in the earlier parts. So then we can rewrite each one back individually into the form, right? XRA can be written as X is an element of the equivalence class of A under relation R, and then the same for S. And then hence when we combine it, since it's the same elements and then there's this intersection, we can just combine the parts like this. So yeah, every step can be reasoned through. Um, for part three, we have for K is natural numbers not including zero, define an equivalence relation TK on N such that A, TK, B, F only F. This holds. Describe the partition of N given by the equivalence class of T4. Okay, so what this means is that if it's something A divided by K and then taking the floor of that, that basically means we're just taking whatever the we're just dividing it by whatever that K is and then grouping the things that have the same kind of quotient together, right? So in the case when it's K is equal to 4, then we just have 4m plus 1, 4m plus 2, 4m plus 3. Four elements combined together, that's part of the partition. And then each one is partitioned like that. And then for the next part, we have describe the partition of N given by the equivalence class of T3 and T4. What this means is that we can just kind of draw out what T3 is. T3 by definition is just 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, right? And it continues on and on. And then T4, as we just talked about earlier, is just these kind of every four, every four, every four, right? So T3 and T4 would look something like this. The partition would look something like this. This is first, on this side, on the left-hand side, I have my T3, and on the left-hand side, I have my on the second term, I have the T4. So basically, when we AND it together, the first one we have three common elements. And the next, this one's done, so I go to 3, 4, 5, and then I AND it, so then I have only one element in common. And then this one's done, so then I now move on to this part, right? And I compare that, and I get this. And I go on and on and on, just to make sure every time, whichever's finished, I just move it to the next one, and I just compare the common elements. And I find this. By the time I get to 11, when I get to 12, I see, okay, this one's starting at 12, this one's starting at 12. And this is no coincidence that the number in each of the partitions, like the size of it, would repeat as before, 3, 1, 2, 2, 1, 3, and then repeat again because um, every time you start off the same thing, right, the loop begins again. And then we can just kind of think of it as Y12, right? It's the lowest common multiple between 3 and 4 because every time you would need to match it up together so that you go back to the same starting point again. So yeah, so 12 is that starting point. So then it would repeat after a pattern with the size of the partition as this. And then we can just further kind of formally write this as we're just having this, and then from this range, we're just going to break it down into basically this is one partition. Every 12 elements, we have a partition. And then inside this partition, we have the sizes of 3, 1, 2, 2, 1, 3 that repeats with this pattern. So that's the idea. So overall, like that takes us to the end of the question. I'd say, yeah, this question was pretty definition heavy. Like part A was completely definition. Um, there was also one part that was like um define. Yeah, CI was definition as well. And then I think there was just like several other parts that were proofs. I think, yeah, CII definitely write the thing more formally, and for C4, part 4, it's definitely, even though you get the intuitive idea relatively easy, but yeah, it's important to write it out formally.